There is a place inside our own galaxy where space has stopped following the rules. Not at some distant edge of the universe, not in some theoretical equation on a whiteboard. Right here, in the same galaxy where our sun burns, where our planets orbit, where every constellation we've ever named exists. A region so vast it spans thousands of light years, and yet every telescope we point at it returns the same answer. Nothing. Not faint, not unclear. Nothing. And the terrifying part isn't the silence. The terrifying part is that the silence has a shape. I want you to sit with that for a second, because when astronomers first started noticing the signal drop out, nobody panicked. Nobody even got particularly excited. Radio frequency mapping is painstaking, methodical work. You build a picture of the sky one frequency band at a time, like developing a photograph in a darkroom, slow and deliberate. And then one section of that photograph refuses to develop. The signal doesn't fade the way it should if dust or gas were in the way. Dust scatters signals gradually, like fog thinning at the edges of a streetlight. This was different. This was a wall. One side of the boundary, normal data. The other side, a clean, hard drop into nothing. The researchers ran the calibration checks again. Then they switched instruments entirely and ran it a third time. The wall was still there, crisp as a cut made with a blade. What followed was the kind of slow-building dread that doesn't announce itself loudly. It just starts occupying space in the back of your mind. Follow-up observations came in infrared, same wall. X-ray imaging, same wall. 3 completely different windows into space, 3 completely different detection methods, all returning the same verdict in the same location. At that point, instrument error is off the table. Atmospheric interference is off the table. What remains, once you've ruled out every mundane explanation, is the thing nobody wants to say out loud in a peer-reviewed paper. Something is in there, and it is actively swallowing information before it can reach us. Not blocking it, not scattering it, swallowing it. Because blocking and scattering still leave traces. Dust leaves absorption lines. Gas leaves spectral signatures. Whatever is inside this region leaves nothing traceable at all. It consumes the signal and returns silence so clean it almost sounds deliberate. And I know how that sounds. I know the word deliberate has no business being used in astrophysics, but when something behaves with that level of consistency across that many independent observations, the human mind starts reaching for intention as an explanation, even when intention is the one thing physics refuses to allow. That instinct, it turns out, may not be entirely wrong, just premature. Because here's what makes this region genuinely different from every other anomaly ever cataloged. It doesn't just block light, it bends it. Gravitational lensing measurements around the boundary showed something that made the data teams go very quiet very fast. The light from distant objects passing near this region curves, not randomly, predictably, with the mathematical precision of light curving around an enormous mass, which means something inside that silent zone has gravity, immense gravity. Gravity that has been doing its work consistently, measurably, and without any visible source for longer than any instrument has been watching. Footprints in the data, no body to make them. And that is the moment this stops being an interesting calibration puzzle and starts being one of the most unsettling open questions in modern science. If you're finding this as mind-bending as I do, subscribe and leave a like. It genuinely helps this kind of deep dive content reach more people, and we're just getting started. Now, before we go any further into what this region might actually be, we need to back up. Because to understand why the silence is so wrong, you first have to understand what silence is supposed to mean in physics. And the answer, once you learn it, rewires something fundamental in how you see the universe. For most of human history, the working assumption was straightforward. Space is empty. Stars and planets are the exceptions, rare bright islands in an infinite dark ocean of nothing. It was intuitive. It matched what we could see. And it was completely, comprehensively wrong. Quantum field theory didn't just poke a hole in that picture. It demolished the foundation. Because what physicists discovered, through decades of increasingly precise experimentation, is that the vacuum, the deepest, most remote emptiness between galaxies, is not empty. It is boiling. Quietly, invisibly, at a scale too small for any conventional detector to catch, but boiling nonetheless. Particles flicker into existence and vanish before any measurement can pin them down. Fields vibrate beneath the surface of detectable reality, the way a guitar string vibrates after the note has faded. Energy still moving, still real, still present even when the sound is gone. This isn't metaphor. This isn't approximation. The Casimir effect proved it directly. Two metal plates placed nanometers apart in a perfect vacuum experience a measurable attractive force produced by nothing more than the pressure difference between the quantum fluctuations inside and outside that tiny gap. Emptiness pushing on emptiness, energy extracted from nothing. And if that already sounds strange, hold that feeling. Because the blind spot in our galaxy exists inside this same seething, never truly empty vacuum. And a region that size behaving with that level of organized, consistent silence inside a quantum vacuum that fundamentally cannot be silent is not an absence. It is something else entirely. Something the universe seems to be working very hard to keep us from seeing clearly. So we've established that the vacuum isn't empty, that it seethes with invisible energy, and that a region of our galaxy is somehow maintaining a silence so clean it shouldn't be physically possible. But here's the thing that took this from strange to genuinely alarming. The silence has a border, and that border does something that no natural process we know of can explain. When you map the edge of the blind spot carefully, tracing it across multiple frequencies and observation runs, you don't find the kind of blurry, irregular boundary you'd expect from a cloud of gas or a dust formation. Those things have soft edges. They dissolve into surrounding space the way cream dissolves into coffee, gradually, unevenly, with no clear line where one thing ends and another begins. The blind spot has none of that. Its edge is sharp, repeatable, consistent across years of observation, from different instruments on different continents pointing at the sky on different nights. And that sharpness is the detail that keeps physicists staring at their data at 2 in the morning with cold coffee going stale beside the keyboard. Because sharp boundaries in space mean structure. They mean something is maintaining that edge, holding it in place, keeping the inside separate from the outside with a kind of discipline that diffuse matter simply cannot sustain over thousands of light years and millions of years. Whatever is inside that region isn't leaking out. Whatever is outside isn't bleeding in. The boundary holds, and the longer it holds, the harder it becomes to explain it as anything passive or accidental. The first serious attempt to explain the boundary used pressure gradients, the idea that some difference in density or temperature between the region and its surroundings could create a stable interface. That idea lasted about as long as it took someone to actually run the numbers. The pressures required to maintain a boundary that sharp at that scale, for that duration, don't exist in any known configuration of normal matter. The second attempt leaned on magnetic field structures, which can create defined regions in plasma, also ruled out because the electromagnetic signatures simply aren't there. One by one, the conventional explanations lined up, took their turn, and were quietly eliminated, until the only thing left standing was the possibility that the boundary isn't maintained by anything inside the region at all, that the boundary is the region, that we're not looking at a container with something inside it. We're looking at a single, unified thing whose outer edge and inner structure are the same phenomenon expressed differently. And that idea has no comfortable home in classical physics. What it does have is a home in quantum field theory, and that is where this story takes a turn that changes everything. Gravity without a source. 4 words that should not be able to coexist in the same sentence, and yet here we are, with the data sitting in front of us, making exactly that case. When the gravitational lensing results first came back clean enough to publish, the team that ran the analysis apparently sat on them for weeks, not because they doubted the measurements, because they doubted what the measurements implied. Gravitational lensing works like this. Mass curves space-time. When light from a distant object travels through curved spacetime, it bends. The amount of bending tells you with remarkable precision how much mass is doing the curving. It's one of the most reliable tools in modern astronomy, verified against hundreds of known objects, calibrated against measurements we trust completely, and when researchers applied it to the boundary of the blind spot, the light was bending significantly, consistently, in exactly the pattern you'd expect from an enormous concentration of mass sitting right where the silent region sits. So they looked for that mass thoroughly. Every catalog of known objects in the region, every archival image, every prior observation that touched that patch of sky, and the inventory came back essentially empty. No dense cluster of old stars, no remnant of a collapsed structure, no concentration of gas massive enough to account for even a fraction of what the lensing required. The gravity was real. The source was not there, and unlike a detective story where the missing piece eventually turns up, this particular absence has only deepened with time and better instruments. More sensitive telescopes have looked. More refined models have been applied. The verdict has not changed. Something is bending space in that region with the force of an immense mass. And that mass has no conventional physical form that we can find. It is, in the most literal sense that physics allows, a gravitational fingerprint with no hand to make it. And here is where your instinct might whisper, dark matter, the invisible scaffolding of the universe, undetectable by light, present everywhere in vast quantities. It seems like the obvious answer. It feels almost too clean, which is exactly why what comes next is so deeply uncomfortable. Dark matter was supposed to be the answer, and for about 48 hours after the lensing results went public in the research community, it probably was the answer in the minds of most people who read the summary. Invisible mass, no electromagnetic interaction, bends space-time, accounts for the missing gravity and galaxy rotation curves across the entire observable universe. It fits, except when you actually sit down and model what dark matter does to a region of space, what shape it takes, how it distributes itself, the fit falls apart completely. Dark matter doesn't do edges. That's the core problem. Dark matter halos, the invisible shells of mass that wrap around galaxies and galaxy clusters, are by nature diffuse. They extend outward in smooth gradients, thinning gradually over enormous distances, with no defined boundary anywhere. If you tried to draw where a dark matter halo ends, you couldn't. There is no line. There is only a slow fade into a background that itself is full of dark matter from other structures, overlapping and interweaving across cosmic distances. It is, by every model we have, fundamentally incapable of forming a crisp, stable, enclosed boundary of the kind the blind spot displays. Asking dark matter to explain that sharp edge is like asking fog to cut glass. It simply isn't the kind of thing the material does. Researchers tried pushing the models anyway. They introduced hypothetical concentrations, local density spikes, configurations that aren't observed anywhere else but might, in principle, produce something closer to a defined region. None of it worked. Every modified model either produced a boundary too soft, collapsed under its own gravitational dynamics before it could stabilize, or required initial conditions so improbable that invoking them was more or less the same as saying, we don't actually have an explanation. After enough of that, the honest conclusion became unavoidable. The blind spot is not a dark matter structure. It is something the field does not yet have a name for, and that namelessness is exactly where things start getting deeply strange. Because once you rule out everything familiar, what you're left with isn't nothing. What you're left with is quantum field theory, sitting quietly in the corner, raising its hand. Quantum fields are not things that exist inside matter. That framing gets it exactly backwards. Matter exists inside quantum fields. Every particle you have ever seen, touched, or measured is an excitation of an underlying field, a ripple in something that was already there before the ripple formed. The electron field, the quark field, the Higgs field, they don't switch off between particles. They fill all of space, all the time, vibrating at their ground state, even in the deepest vacuum, even in regions where no particle has ever been detected. And under the right conditions, those fields don't just vibrate, they organize. This is the idea that physicists find genuinely hard to discuss in public without sounding like they've lost their footing. Because what quantum field theory allows, mathematically, rigorously, without any hand-waving, is a stable configuration of field states that has mass, that curves space-time, that exerts gravitational influence on everything around it, and that emits absolutely nothing. No photons, no radio waves, no X-rays, no signal of any kind that any instrument built to detect particles would ever catch. Not because it's hiding, not because it's shielded, but because it isn't made of particles in the first place. It's made of the space between particles, of the ground state itself, reorganized into something that behaves like matter without being matter in any sense we have a clean word for. And the scale of the blind spot, thousands of light years across, stable across millions of years, with precise gravitational influence and a defined boundary, fits that description with an accuracy that is either deeply meaningful or the most extraordinary coincidence in the history of science. There is no instrument currently in existence that can directly detect a structure like this, not because we haven't tried hard enough, but because every instrument we build is designed to catch particles or radiation, and a quantum field configuration that sits below the particle level is, by definition, invisible to all of them. We built every eye we have to see a certain kind of light, and this thing doesn't use light. It doesn't use anything we built eyes for. It simply sits there, massive and organized and silent, doing exactly what it does, regardless of whether we can see it. And that indifference is the most unsettling part of all. The universe has changed state before, completely, irreversibly, and we have the physics to prove it happened. We just prefer not to think about what that means for right now. Here is a concept that sounds abstract until the moment it clicks, and then it never lets go. In physics, a phase transition is when a substance reorganizes its entire internal structure without changing what it's made of. Water becomes ice, not different atoms, same atoms, completely different behavior, completely different properties, and a sharp boundary exactly where the transition occurred. The boundary between ice and water isn't a mystery. It's the physical record of where one set of rules ended and another began. Now take that idea and apply it not to water, but to space itself. Quantum field theory doesn't just allow for one vacuum state, it allows for multiple. The vacuum we live in, the one that produces the quantum fluctuations we measured with the Casimir effect, the one our particles and fields and chemistry all depend on, is one possible configuration of the underlying quantum reality. But it may not be the only stable one. There could be deeper states, lower energy configurations that space itself could theoretically settle into under the right conditions. And if a region of space made that transition, if it dropped into a different vacuum state, what would it look like from the outside? It would look like an absence, a region where the internal rules had shifted, where the fields that normally produce detectable particles and radiation were reorganized into a configuration that our instruments, built for this vacuum, cannot read. It would have mass, it would bend space-time, it would maintain a defined boundary exactly where the transition occurred, crisp and stable, the way the edge of an ice sheet is crisp and stable against liquid water, and it would be completely, perfectly silent to every telescope we own. The blind spot matches this description so precisely that the match itself becomes a kind of evidence, not proof. Science doesn't work in proof. It works in weight of evidence. But the weight here is not trivial. A phase-changed region of space would look exactly like what we are observing, and the terrifying implication sitting underneath that statement is this: if such a transition already happened once, right here in our own galaxy, then space is not the stable, uniform backdrop we assumed it was. It is a medium with multiple possible states, and we are living inside one of them, with no guarantee that it is the only one that can persist. That thought has a particular quality to it, not sharp panic, more like the feeling of standing in a room and suddenly noticing that the floor has a crack running all the way across it that you somehow never saw before. The room hasn't changed, but you have. Now here's what pulled this out of pure theory and planted it firmly in observable reality. The stars. Not the stars inside the blind spot. We can't see those, if there even are any. The stars around it. Specifically, the stars moving along its boundary, close enough to feel its gravitational influence, far enough to still be visible to us. Researchers began tracking their motion carefully, building velocity maps over years of observation, watching which direction each star was drifting and how fast. And what came back was not the scattered, irregular motion you'd expect if those stars were simply responding to the general gravitational background of the galaxy. It was organized, coordinated. Stars on the near edge of the blind spot were curving in their paths in a way that implied a shared gravitational center, something anchoring them all from the same point, pulling each one along a trajectory that only made sense if something massive and stable was sitting right at the heart of the silent region. The precision of those orbits is the detail that stops people mid-sentence when they first encounter it, because precision in orbital mechanics requires consistency. A gravitational source that wobbles, drifts, or fluctuates over time produces messy orbits that diverge and spread. These orbits weren't messy, they were clean, reproducible across observation periods spanning years, implying that whatever is at the center of the blind spot has been sitting in essentially the same configuration, exerting essentially the same gravitational influence, with essentially the same stability, for a span of time that makes human civilization look like a rounding error. Not decades, not centuries, millions of years of uninterrupted gravitational consistency from a source that has never once emitted a single particle of light. And that word, organized, keeps coming back, because organization at that scale, sustained over that duration, is not something that happens by accident in physics. Chaotic systems don't self-maintain over millions of years. They decay, they disperse, they lose coherence. The fact that the blind spot hasn't done any of those things means that whatever it isn't just sitting there passively. It is, in some sense that we don't yet have the right language to describe, holding itself together, actively, continuously, across timescales that challenge every assumption we have about what naturally occurring structures in space are capable of doing. Which raises a question that nobody in the field phrases out loud very often, because the phrasing sounds wrong no matter how carefully you choose the words. If this thing has been maintaining its own coherence for millions of years, what exactly is doing the maintaining? 2 points in space, separated by a distance so vast that light takes years to cross it, sharing a single quantum state as if the distance between them simply does not exist. That is not a metaphor. That is a laboratory-verified, experimentally repeatable fact. And it is the next piece of this puzzle that nobody quite knows how to fit into the picture without the picture changing completely. Quantum entanglement gets described in popular science as a curiosity, a quirk of the subatomic world that has no relevance at human scales, let alone galactic ones. That framing has been quietly falling apart for years, because the same mathematics that describes entanglement between two electrons in a lab also appears, unbidden, in the equations that describe how space-time itself holds together. Some of the most serious theoretical work being done right now suggests that the geometry of space, the fabric that everything we can see and touch and measure is embedded in, may itself be a product of entanglement. That what we experience as distance, as the separation between 2 points, is actually a kind of relationship, a correlation between quantum states. And correlations can span any distance without violating any physical law, because they aren't traveling through space. They are the structure that space is made of. Now bring that idea back to the blind spot. If the region is not a localized object sitting at a specific set of coordinates, but rather a network of entangled quantum states distributed across thousands of light-years of space, then looking for it in the traditional sense is exactly the wrong approach. You cannot point an instrument at a relationship. You cannot photograph a correlation. You cannot measure the position of something that exists between positions rather than at one. The blind spot, in this framework, isn't hiding from our telescopes because it's far away or faint or obscured. It's beyond the reach of our telescopes in a more fundamental sense, because our telescopes are designed to find objects, and this is not an object. It is a condition. A state that space itself is in, across an enormous region, invisible to every tool built on the assumption that the thing you're looking for is somewhere specific. And that reframing, from whole to hub, from void to network, changes the emotional texture of the whole mystery. Because a void is passive. It just sits there. But a hub does something. A hub connects. A hub processes. A hub is, by definition, the kind of structure that the rest of the system depends on without necessarily knowing it. And the idea that the blind spot is not an emptiness the galaxy happens to contain, but a node that the galaxy is in some sense organized around, is the kind of idea that once it lands, you can't quite see the night sky the same way afterward. The question that follows immediately is the one that takes us somewhere even more uncomfortable. If we can't see it, can't isolate it, can't probe it directly, how do we know it's real and not just a gap in our data that we've been filling with increasingly elaborate theory? And the answer to that question is the same answer physics has given every single time it encountered a wall this high. We know because of what happened before. Not once, not twice. Every major revolution in our understanding of the universe was preceded by an anomaly that the existing framework could not absorb. A number that didn't add up, a measurement that kept coming back wrong, a gap between what the theory predicted and what the instruments found, persistent, reproducible, and stubbornly resistant to every conventional fix applied to it. The discovery of neutrinos began as missing energy in a decay process that the math said should have been conserved. For years, the measurements were trusted more than the explanation, and the explanation turned out to require an entirely new category of particle that had never been imagined. Dark matter began as galaxies rotating too fast for the visible mass they contained, a discrepancy that most astronomers initially assumed was an error. It wasn't an error. It was the universe pointing at something the model had left out. In both cases, the anomaly wasn't a flaw in the data. The anomaly was the discovery, waiting for a framework capable of receiving it. The blind spot is producing that same signal right now. The gap between what we observe, organized gravity, stable boundaries, total silence across all frequencies, and what every existing model can explain, is not narrowing with more data. It is widening. Each new observation confirms the anomaly rather than dissolving it. Each refined measurement makes the contradiction sharper rather than softer. And in the history of physics, a contradiction that sharpens with scrutiny has never once turned out to be nothing. It has always turned out to be the edge of the next thing we did not yet know how to see. Which means the blind spot isn't a problem waiting to be closed. It is a door. And the question now is not whether something is on the other side of it, but whether we are ready for what opening it might require us to give up. What if the reason we can't observe the blind spot isn't a limitation of our instruments, but a feature of the blind spot itself? What if it stays hidden, not despite our attempts to find it, but precisely because of them? This is not a philosophical riddle. It is a direct implication of one of the most well-tested frameworks in all of science. Quantum mechanics tells us that certain systems don't have fixed properties until the moment of measurement, not unknown properties, genuinely undefined ones. The particle doesn't have a position until something interacts with it and forces a resolution. Before that interaction, it exists as a spread of possibilities, a blur of potential states, none of them real in the classical sense, until contact collapses them into one. And here is the part that most explanations quietly skip over. Some systems, when you try to measure them too aggressively, don't just refuse to give you a clean answer. They decohere. The very act of probing them destroys the coherence that made them interesting in the first place. You reach in to grab the thing, and the thing dissolves into noise before your hand closes around it. Now consider what every observation attempt aimed at the blind spot actually involves. Electromagnetic radiation traveling through the region and failing to return. Instruments sending signals and receiving nothing back. Every method we use to observe space is, at its core, an interaction. We bounce something off the target and measure the result. But if the blind spot is a quantum structure operating at the level of the vacuum state itself, then every probe we send into it is not a neutral act of observation. It is an interaction with a system that may respond to interaction by becoming less coherent, not more. We point our best instruments at it and get silence back, and we interpret that silence as a lack of information. But there is another interpretation, that the silence is information, that the system is telling us, in the only language available to it, that this particular method of looking will never work. Not because the technology is insufficient, but because the question is being asked the wrong way. There is a concept in quantum mechanics called the quantum Zeno effect. If you measure a quantum system frequently enough, you can actually freeze its evolution. The measurements themselves hold it in place, which means that a region of space being continuously observed, mapped, probed across multiple frequencies by multiple instruments across decades of study could theoretically be locked into a particular behavior by the observation itself. Not stable because of its internal structure alone, stable partly because we keep looking at it in the same way, with the same assumptions, reinforcing the same outcome every time. We may be, without realizing it, participating in the thing we are trying to understand, and that possibility sits at the edge of what physics can currently say, without tipping into territory that requires entirely new mathematics to describe. What it does not sit at the edge of is plausibility. It is entirely plausible, and that is exactly what makes it so hard to dismiss. There is a scenario that physicists return to when they want to illustrate just how fragile the ground beneath us really is, and they almost always introduce it carefully, with appropriate qualifications, in the tone of someone who would rather not be having this conversation at all. The scenario is called vacuum decay, and it goes like this. The vacuum state our universe currently occupies may not be the lowest possible energy state available to the underlying quantum fields. It may be what physicists call a metastable state, stable enough to persist for an enormous span of time, but not the deepest resting point the system could theoretically reach. Like a ball sitting in a shallow valley on the side of a hill, it stays put as long as nothing disturbs it, but if something nudges it over the edge, it rolls, and it doesn't stop rolling until it reaches the lowest point available. In the case of the universe, that rolling would take the form of a bubble of true vacuum, expanding outward from the point of transition at the speed of light, rewriting every physical law inside it as it goes. The fundamental constants that allow atoms to form, that allow chemistry to exist, that allow stars to burn and planets to hold together, all of them replaced by a different set of rules, tuned to a deeper energy minimum. No warning, no observable approach, just a boundary moving at the speed of light, and then a different universe on the other side of it. Nobody is claiming this has happened in the blind spot. That is the important qualification to hold on to. But the blind spot has forced this scenario back onto the table in a very specific way. Because for vacuum decay to be purely theoretical, we need space to be uniform. We need the vacuum state to be the same everywhere. The blind spot is evidence that it may not be. That different regions of space can settle into different configurations of the underlying fields. And if that is true, then the question of whether our local vacuum state is genuinely stable or merely hasn't been disturbed yet is no longer purely academic. It becomes a question about the ground we are standing on, right now, in this galaxy, around this star, on this planet that has, so far, been extraordinarily lucky in its physics. Everything we've discussed so far assumes the blind spot is something inside the galaxy, a region, a structure, a thing located at a set of coordinates that we simply haven't been able to pin down yet. But what if that assumption is the mistake that has been slowing us down from the very beginning? Think about how we locate anything in space. We find it by what it does to the space around it. A star is where the light comes from. A black hole is where the surrounding gas spirals inward. A galaxy cluster is where the background light bends. Every object we have ever cataloged in the history of astronomy has been identified by its relationship to the space surrounding it, by the signature it leaves on the medium it sits inside. But the blind spot doesn't leave that kind of signature. It doesn't sit inside the space around it the way an object does. Instead, the space around it behaves differently because of it, in a way that feels less like the influence of an object and more like the influence of a rule, a constraint that the local geometry is operating under. The way a coastline shapes the ocean, not because it sits inside the ocean, but because it defines where the ocean is allowed to go. This reframing sounds subtle until you trace its implications, and then it becomes one of the most disorienting ideas in this entire story. Because if the blind spot is not a thing in space, but a condition of space, then the instruments we use to find things in space are not just insufficient, they are the wrong category of tool entirely. We have been searching for a noun when the answer is a verb, looking for an object when what we are actually dealing with is a behavior. And that distinction explains, with uncomfortable elegance, why every direct observation attempt has returned nothing. You cannot photograph a rule. You cannot point a telescope at a constraint. You can only observe its effects on everything that operates within it. And that is exactly what we have been doing, without realizing it, for years. The stellar orbits at the boundary are not evidence of an object, they are evidence of a condition. The gravitational lensing is not a fingerprint of a body, it is the visible impression of a geometry that has been locally modified. The silence across all frequencies is not the silence of something hiding. It is the silence of a region where the rules that produce detectable signals are operating differently. Every observation we have made of the blind spot has been correct. Our interpretation of what those observations mean has been the error all along. And the moment that realization settles, the question changes completely. Not what is inside the blind spot, but what role does this condition play in the larger structure of the galaxy? And that question has an answer that nobody anticipated, and that answer is stranger and in some ways more comforting and in other ways more unsettling than anything that came before it. The universe is not a simple machine. It is an enormously complex system that has been running for longer than any number expressed in ordinary language can meaningfully convey. And complex systems, without exception, require regulation. They require mechanisms that absorb instability, that contain the configurations that would otherwise propagate and destabilize the whole, that allow the predictable parts to stay predictable by quietly managing the unpredictable parts somewhere out of the way. In a living cell, this is done by proteins that fold and unfold in response to chemical signals, catching misfolded molecules before they can aggregate and damage surrounding tissue. In a power grid, it is done by regulators that absorb voltage spikes before they can cascade into a blackout. In quantum computing, it is done by error correction codes, deliberate redundancies built into the system that protect the fragile, useful information from being corrupted by the noise that is always, inevitably, trying to creep in. The useful computation happens in one layer, the error correction happens in another. And the two layers never directly interact in a way that lets you observe the correction from inside the computation. The blind spot may be performing an analogous function for the galaxy, not storing matter, not emitting energy, not doing anything that looks from the inside like action, but absorbing the quantum configurations that would otherwise propagate into the surrounding space and degrade the conditions that allow stable chemistry, stable stellar evolution, stable long-term structure of any kind, holding the exceptions, containing the contradictions, functioning as a pressure valve for a system that would otherwise have no way to shed the instabilities that accumulate over millions of years of complex physical processes running simultaneously across billions of stars. And the reason this has to be hidden, the reason it cannot announce itself with detectable signals, is precisely because a regulator that can be interfered with is a regulator that can fail. The most important systems in any complex structure are the ones you never see working, the ones that only become visible when they stop. And the blind spot has not stopped, not once, not in all the time we have been watching, which either means it is functioning exactly as it should, or it means the failure mode, when it eventually comes, will not announce itself in advance. That thought has a very specific texture to it, not immediate alarm, something quieter. The feeling of realizing that the stability you have always taken for granted is not a given, it is a product. Something is producing it, and you have been living your entire life inside the output, without ever once wondering about the machinery. The universe has been expanding since the moment it began. That much we've known for a long time. But here's the part that keeps physicists awake. It's not just expanding, it's accelerating. The galaxies aren't just moving apart, they're moving apart faster and faster, as if something is pushing them, as if space itself is developing an appetite for more space. The name we gave this force is dark energy, and that name is, in the most honest possible reading, a confession. We called it energy because it has effects. We called it dark because we have absolutely no idea what it is. For decades, dark energy has been treated as a background constant, a fixed property of space itself, uniform everywhere, unchanging over time, woven into the fabric of the universe like a tension that never relaxes. The Standard Model depends on this uniformity. The calculations that predict how galaxies cluster, how the cosmic web forms, how the large-scale structure of the universe evolves, all of them assume that dark energy is the same everywhere and has always been the same. And those calculations have matched observations well enough that the assumption was never seriously challenged, until the blind spot forced the challenge. Not directly, not with a single dramatic measurement that broke the model, but with a slow accumulation of background data that doesn't quite fit. Surveys of how fast different regions of the universe are expanding have started returning results that disagree with each other at a level that should not be possible if dark energy is truly uniform. Different patches of sky, measured with different instruments using different methods, give slightly different values for the expansion rate. The discrepancy is small enough that it spent years being attributed to measurement error, but it has persisted, and it has persisted in a way that correlates, imperfectly but noticeably, with the distribution of regions in the universe that behave anomalously, regions that in some cases share characteristics with the blind spot, defined boundaries, gravitational influence without visible source, silence across multiple frequencies. What this suggests, and the word suggest is doing a lot of careful work in that sentence, is that dark energy may not be a fixed background at all. It may be a dynamic quantity, something that varies across space in response to the distribution of quantum structures embedded in the fabric of the universe. And if the blind spot is one of those structures, one node in a much larger network of hidden regulators spread across the cosmos, then the accelerating expansion is not a simple push applied uniformly to everything. It is the visible surface of a redistribution, a rebalancing of vacuum energy across cosmic scales, mediated by structures we can't see directly, producing effects we have been measuring for decades without understanding their source. That interpretation doesn't just change what dark energy is, it changes the entire picture of what the universe is doing and why, and it points toward a conclusion that feels almost too large to hold in a single thought, that the blind spot is not an isolated anomaly in one corner of one galaxy. It may be a single, readable example of a class of structures that together determine the long-term fate of everything. And we found it not because we were looking for it, but because it left just enough of a mark on the space around it for us to notice something was wrong. There is a question that this entire investigation keeps circling without quite landing on, and it is the one that shifts this from a story about physics into something that feels almost personal. Why do we exist at all? Not in the religious sense, not asking about meaning or purpose, in the purely physical sense. Why does a universe that operates on quantum principles, where uncertainty is fundamental and coherence is fragile, produce stable structures complex enough to develop chemistry, then biology, then nervous systems, then minds capable of sitting here and asking questions about their own existence? The standard answer is time and scale. Given enough time and enough space, probability produces complexity. Random processes exploring enough configurations eventually stumble onto stable ones, and stable things persist while unstable things don't. That answer is true as far as it goes, but it leaves something out. It doesn't explain why the background conditions that allow complexity to develop are themselves so precisely tuned. Why the constants of physics sit in the narrow range that permits atoms to form, and stars to burn, and carbon to exist in the first place. The standard answer to that is usually the observation selection effect. We can only ask the question in a universe where asking is possible, which is logically airtight and intellectually unsatisfying in equal measure. But the blind spot opens a different angle on this question, one that doesn't require selecting from an infinite ensemble of universes or appealing to coincidence. If structures like the blind spot function as regulators, absorbing the quantum noise and instability that would otherwise degrade the conditions that complex chemistry needs, then complexity is not just a lucky outcome of random exploration. It is a downstream product of a system that was already, in some sense, managing the conditions necessary to produce it, not designed, not intentional, but structured, arranged in a way that funnels the universe towards states where intricate things can persist, and minds capable of noticing this, capable of looking up at the night sky and feeling the particular weight of a question that has no comfortable answer, are not accidents floating in a cold, indifferent void. They are what the system eventually produces when the regulation holds long enough, and the conditions stay stable long enough, and the chemistry gets complex enough to start asking why. That thought lands differently than most ideas in physics. It doesn't resolve the mystery, it deepens it, because if we are, in some structural sense, a consequence of the blind spot doing its job, then understanding what it is stops being purely academic. It becomes something closer to understanding the conditions of our own existence. And that is a question that has a very different kind of urgency to it than any purely scientific puzzle. It is the kind of question that once you hear it clearly, you cannot quite stop thinking about. We have been studying the blind spot for long enough now that the data has started to do something unexpected. It has started to accumulate into a shape, not the shape of the thing itself. We are no closer to seeing inside it than we ever were, but the shape of its influence, the outline of what it does to everything around it. And that outline, built from years of stellar motion tracking and gravitational mapping and anomaly cataloging across multiple research teams, who often didn't know the others were working on the same problem, has begun to look less like a random gap in the data and more like a signature, consistent, repeatable, specific enough to be recognizable. This is how the next phase of research began, not with a single breakthrough observation, but with a comparison. Someone placed the gravitational influence profile of the blind spot next to anomaly data from a survey of distant galaxies, structures far outside our own, and noticed that certain regions in those galaxies produced a profile with the same basic shape, not identical, scaled differently, oriented differently, embedded in different galactic environments, but structurally similar in the way that two different coastlines can be structurally similar even if they don't look alike at first glance. The same pattern of influence, without visible source, the same sharp boundary behavior, the same silence across the frequencies where something that size should be loudly announcing itself. The implication arrived slowly, the way the most important implications always do. If the blind spot has a recognizable signature, and that signature appears in other galaxies, then this is not a local accident. It is not a quirk of our particular corner of the Milky Way, or a product of some unusual event in our galactic history. It is a recurring feature, something the universe produces, somewhere in this class of structure, with enough regularity that it shows up across galactic distances in environments with completely different formation histories, a repeating motif in the architecture of space. And repeating motifs in physics are not coincidences. They are laws waiting to be named. What this means practically is that the question we have been asking, what is the blind spot, is about to become a much larger question. Not what is this one anomaly in our galaxy, but what is this class of structure? How common is it? How does it form? What role does it play in the long-term evolution of galaxies in general? And what does its existence tell us about the deep architecture of the universe that produced it everywhere it appears? The blind spot in our galaxy was the first page of a text we are only now realizing is a full book, and the reading of it has barely begun. There is something quietly extraordinary about the fact that we found it at all, given that it emits nothing, given that it resists direct observation, given that every conventional tool we use to study space was built on assumptions that this structure violates. The fact that human curiosity, patient enough to keep mapping a region that kept returning nothing, sharp enough to notice that the nothing had a consistent shape, found it anyway, is itself a kind of answer to the question we raised earlier about why minds like ours exist in the first place. Here is where everything in this story lands. Every idea we have explored, every anomaly, every failed explanation, every uncomfortable implication, it all converges on a single recognition that is simple to say and takes a long time to actually absorb. The universe was never obligated to be understandable. Think about that seriously for a moment. The laws of physics that allow atoms to form, that allow stars to burn, that allow chemistry and biology and nervous systems to develop, none of those laws contain any requirement that the beings they eventually produce should be able to comprehend them. Understanding is not written into the contract. Curiosity is not guaranteed a return. And yet, here we are, capable of detecting the gravitational shadow of something we cannot see, capable of inferring the shape of a structure from the behavior of stars orbiting its edge, capable of reading the outline of a mystery from the data it leaves behind, even when the mystery itself refuses to open. That capacity, the ability to know the shape of something we cannot directly observe, is not a small thing. It is not a consolation prize for failing to see inside the blind spot. It is, in a very real sense, the most sophisticated thing any known form of matter in the universe has ever done. We are configurations of atoms that the universe produced, that learned to ask questions about their own origin, and that are now mapping the hidden architecture of the galaxy they live inside. Not because the universe invited us to, not because the answers are guaranteed, but because the questions themselves turned out to be unavoidable. The blind spot does not care whether we understand it. It has been doing what it does for longer than our planet has existed, and it will continue doing it long after every telescope we have ever built has gone dark. Its stability is not dependent on our observation. Its function is not interrupted by our confusion. It simply continues, massive and silent and precisely organized, shaping the conditions that allowed us to arise in the first place, indifferent to whether the thing it helped produce ever figures out what it is. And that indifference is not cold, it is just honest. The universe does not withhold its secrets out of cruelty. It withholds them because some structures exist at a level deeper than the one where explanation is possible. The blind spot is not a puzzle with a missing piece. It is a reminder that the map is not the territory, that the deepest features of reality are not required to fit inside the frameworks we build to describe them, and that the appropriate response to a mystery this fundamental is not frustration. It is the particular kind of focus that comes from knowing you are standing at the actual edge of what is currently knowable, looking outward. So here is the question I want to leave you with, and I mean this genuinely. I'd love to know what you think. If the blind spot turns out to be a regulatory structure that helps maintain the conditions necessary for life to exist in this galaxy, then learning more about it, probing it more aggressively, potentially disrupting it, carries a risk we have never had to consider before in the history of science. Does the value of understanding something justify the risk of destabilizing the very conditions that made understanding possible? Where is that line, and who gets to decide when we've crossed it? Write your answer in the comments. I'm genuinely reading them. And if this kind of deep, unresolved, genuinely unsettling science is what you come here for, subscribe and leave a like. It's the clearest signal you can send that you want more of exactly this.